So now that we've covered descriptive statistics, the sort of natural progression is to talk about the very basics of inferential statistics. So we're going to sort of go back to that same motivating problem that we had in descriptive statistics. We started with how can we answer this question of are you tall, or how tall are you as an individual? And that's really easy to answer. You maybe know approximately how tall you are, but it gets harder to answer that question if I ask, is your FYS section tall, right? How do you answer that question about a big group of people with different heights? And that question is, again, progressively to answer if I asked you if the entire first year class was tall. And as we move to bigger and bigger groups, this question gets harder to answer, even with descriptive statistics. So if we think about if students at Cornell are tall, that would be a huge amount of people, right? There's over 1,000 students at Cornell. How do we know how tall students at Cornell are? So there's a lot of obstacles to answering this question. So say we decided that we were actually just going to measure how tall, measure the heights of every student at Cornell. That would take a really long time. It would take a long time to measure everyone. You'd have to wait in line. You'd have to have volunteers to do the measuring. Students might forget to show up and get measured. And right now, not everyone's living on campus. Say we decided to just ask people their heights. Well, maybe not everyone knows their heights, right? This gets over how long it would take, but maybe people don't know exactly how tall they are. And if we were taking a survey, right, we wouldn't get 100% of the students to respond. So as we sort of try to answer these questions with descriptive statistics about bigger and bigger groups, it's not feasible to actually have all of the data that we need, right? So this is sort of a trivial example, but if you can think about, when we have large populations that we want to study, it's not actually possible to get data on every single one of those people. It's even hard to get data on relatively small groups of people. So this is why we have inferential statistics. So the core of inferential statistics is we have this big group that we want to know about, this population. And we can't possibly get all of their information. So instead, we're going to take just sort of a subgroup of this population. And we're going to get the data for them. And we're going to try to figure out how well what we know about this group can tell us about the larger group. So to estimate the heights of all of the students at Cornell, which is our population, we measure just the height of a small subset of the student body, which is the sample, right? So the population is this larger group that we want to know something about, but we can't know the exact truth for that population for lots of different reasons. So instead, we're going to look at just a subset of that group, and we call that a sample. And we're going to figure out the descriptive statistics for that sample and figure out what that can tell us about the population. So the core of inferential statistics, as opposed to descriptive statistics, is making inferences or estimates about a population based on a sample, and then evaluating how certain we are about them. So the relationship between inferential statistics and descriptive statistics is that often this involves calculating descriptive statistics about a sample and then evaluating if we think those are a good estimate for the population. So if we took a sample of students at Cornell, we measured their heights, and we took the average height, we, in inferential statistics, are then going to estimate how well we think that sample average, how well that reflects the population average, which we don't actually know. So this is actually how we calculate lots of things in real life. So in the previous video, I used real data on what we know about, or real estimates about US adult heights. And we don't know what the actual population average height is, right? Because we have never measured every single American at any point in time to know exactly how tall Americans are, right? That'd be incredibly complicated and it's impossible. So what happens instead is the CDC actually conducts a survey of about 20,000 Americans who come in for a doctor's appointment and a physical, and they collect all of this biological data, including measurements, including height, for these 20,000 individuals. So this is a snapshot of the report they put out, and this is how we know what the average height for an adult woman in the U.S. is. There's about 5,500 adult women who are part of this sample, and we use their data to estimate the average height and all of these other statistics for the entire adult female population in the US. So this is based on a sample, and we want to know about the population. So if you notice in this red circle, this first number is 5,547. That's how many women are in this sample. And then we have the mean, right? This is a descriptive statistic. It describes a measure of location, a measure of center for this sample. So the mean was 63.7 inches. But then we also have this thing over here that's the standard error of the mean. And so this is like an additional piece of information in inferential statistics that's going to tell us how certain we can be that this sample mean reflects the population mean, which we don't actually know. We have no way of knowing. So we encounter this all the time, especially right now, like during an election season. We encounter, we're going to call them margins of error, and that's sort of the most common language used. You encounter these all the time. So anytime you see a poll come out, so this is from Grinnell College in Iowa, and this is a poll from just yesterday, that September 2nd, that shows Joe Biden's lead over Donald Trump. And you'll notice that at the top, above this pie chart, it gives a margin of error of 3 to 4 percentage points. So when you see sort of survey results like this, a lot of times they report a margin of error. Right, so these are very common in surveys. This is the survey results from a firm called Morning Consult that polled Netflix viewers about characters from Tiger King. And you can see that they also, it's down here in the corner and I'm covering it up, but they report a margin of error for their survey as well. So you see these a lot, and people talk about them a lot, especially when it comes to polling in politics. They talk about these margins of error. So what does this actually mean? At the heart, these margins of errors are telling us sort of how certain we can be about these estimates. So we're going to use this example from Tiger King because it's more fun. This is from a really prestigious polling firm called Morning Consult, so we know that they are calculating this in a pretty rigorous way. So zooming in here, on this poll conducted in early April among 484 U.S. adults who watched some or all of Tiger King. So we're going to look at Joe Exotic as an example, but they report this margin of error of plus or minus 4%. So what does that mean? This is going to help us determine how certain we are about this estimate, right? So we're going to zoom in again on Joe Exotic in particular to sort of flesh out this one example. So Morning Consult reports that Joe Exotic had an approval rating of 47% with a margin of error of 4%. So this 47% estimate is based on the sample of 484 adults. So the first thing you need to do is use this margin of error, which is 4%, to calculate an interval centered around the estimate, which is 47%, by adding and subtracting the margin of error. So for Joe Exotic, that gives us an interval from 43% to 51%, right? So in this sample of 484 adults, 47% of them approved of Joe Exotic, right? And then when we use the margin of error, we get this interval that's 43% to 51%. What does that mean? This interval is usually associated with some sort of confidence or certainty level. A lot of times it's 90 or 95%. And you'll hear people interpret this as, we can say with 95% confidence or 90% that the true percentage of the population that approves of Joe Exotic is between 43 and 51%. That is, we're 90% or 95% based on how certain they want to be. We're 90% sure that the actual percentage of people in the population who approve of Joe Exotic is between 43% and 51%. That's sort of a weird concept. So I want to talk about where that comes from a little bit. So imagine that this is the population of all viewers of Tiger King. And in each of these boxes is a separate sample that Morning Consult could have drawn. And a hypothetical sample, right? And they only actually draw one of these. But for each of these hypothetical samples, had they actually conducted the poll 10 different times, you would have gotten 10 different estimates and 10 different corresponding intervals. So if we say that we're 90% sure that the margin of error interval contains the true population estimate, that means if we constructed 10 different intervals like this from 10 different survey samples, that 9 of them would contain the correct, 9 of those intervals would contain the actual population number that we're interested in. So say the true proportion of the population that approves of Joe Exotic is 45%. You can see that 9 of these intervals contain that number, right? But it's important to note that one interval doesn't actually contain the true population number that we're interested in, which is the percentage of people who watch Netflix and watch Tiger King on Netflix that approve of Joe Exotic. And so we don't actually know if that's the one we got. We can only say that we're 90% confident that the real number is in our interval. And that basically protects us because we don't know if we got that, the survey we did happened to be that one interval doesn't contain the true population number. All right. So this is sort of an important point because a lot of times when we talk about, especially polling numbers for presidential elections, people will sort of flesh out this, the margin of error, and they'll create this interval and they'll be like, yes, well, it's definitely going to be, the real number is definitely in this interval. But that's not true. People will construct up to 99% intervals. But you can't get an interval that you are 100% sure contains the true population estimate unless it contains literally every possibility. So that's sort of the important concept here that that underlies where this margin of error comes from, and that even when you widen that interval, it's not a guarantee that you actually have captured the true population number that you're interested in. So to review, inferential statistics are all about evaluating how sure we are that our descriptive statistics about a sample are correct for the population. So in particular, we've talked about the margin of error, which is commonly what we see reported in polling, but it's also used in a lot of different things that we think of as like very sort of serious objective measurements. So when we talk about knowing the average height or the average weight of Americans, it's always based on taking a sample from the entire population, because surveying the entire population or getting that data for the entire population is often not feasible. So that's why we have these reported margins of errors. So you add and subtract that reported margin of error. You often see it as like plus or minus some number from the sample estimate, and that creates an interval. And to interpret that interval, the sort of complicated but correct interpretation is that if we drew more samples and calculated the margins of error for each sample, some percent of those intervals would contain the true value. And so we can be certain that our interval, how certain we can be that our interval that we do have contains the true value. So often researchers will decide how confident they want to be. That number is often 90 or 95%. So when you calculate out that interval, you say, we're 95% sure that the true population number is in this interval, which we derived from doing some descriptive statistics on our sample. All right. So that is it for inferential statistics. But the biggest takeaway is that the goal of this is we can't measure something for a population. We can measure it for a sample. and we want to know how good that estimate is for the entire population.